Same exact principle, right? If I just put that there, the derivative of that would give you cosine of negative 2x, but then you'd have a negative 2 pop out because of chain rule. We don't want that negative 2 there, so we put a negative 1/2 to kill off the negative 2, right? And from this, couldn't we just come up with like an arbitrary like formula?
Probably.
Yeah?
Does this only work with like the linear variables? Like if it was like x squared, would that work?
I think that's a question you should think about. Everyone should think about. Is it important that what's in there is linear? Let's continue. I'm going to get to that actually. What would be a generalization of this? Cosine of, I'm generalizing. I don't want to put 3 in there, negative 2. Something in front of x, right? Let's go with a, right? A is usually a good constant. Ax, right, like this. So if we have that, the antiderivative of that should be what? 1 over a sine of ax plus c. Do y'all buy that? If a is a constant, this is like a formula now, right? So to your question, this is linear, right? That's a linear expression. Will it work for any linear expression? Should. As long as it's linear, it should. Like this. Look at this one. That's what we have this formula, right? But what if it was anything linear? What if it was this is linear, right? Some number in front of x plus some number. That's a linear expression. Is that, this is a question, is the antiderivative of that still 1 over a sine of ax plus b plus c? No? What's the derivative? Okay, what's the derivative of this right here? Cosine of this, right? Right? Times, what's the derivative of what's inside? A, and then you're killing it off. You see, the derivative of what's in here, the derivative of ax is a. The derivative of b is 0. So we can actually tack a b onto this formula and it changes nothing. Like, it still works. Linear, it works. Let me give you one more example. This is it right here. I'm going to put a star next to that. That's kind of like the main thing I wanted to take away from this. So if we have this, what's the antiderivative of cosine of that linear expression? Without doing any substitutions, we should understand that first the answer is going to be sine of negative 4x plus 7 plus c. And then we have to think about killing the negative 4 that's going to come out of the chain rule. So we got to have a negative 1/4 out front. And it doesn't matter if you put the negative on top or the bottom. It's a negative, so it should kill it off. That makes sense to everyone? We're just kind of seeing if we can come up with like a generalization. I'm still going to entertain your question. Just let me go another step here. Could we do the same thing for sine? Antiderivative of sine.
You have to put a negative sign, right?
You would have to include a negative, right? So if I had antiderivative of sine of ax plus b, right? The formula for that, well, the antiderivative of sine is not cosine, it's negative cosine, right? So I would need a negative. Then I would need cosine of ax plus b here, plus some constant. But I'd still have to kill off the a that pops out when I do chain rule here, so I'd need 1 over a. So it's exactly the same concept as this one, except we have to throw the negative in front. Does that work for all functions you've ever learned that you know the antiderivative of? Well, I'm saying, does this work for all functions that you know the antiderivative of already? So like this one. Look at this right here. 1 over 4x plus 1 dx. Look at the denominator there. It's linear, isn't it? So this kind of looks like 1 over u. Yes? What's the antiderivative of something like that? Natural log absolute value of u, right? So what goes in here? 4x plus 1 plus c, right? But am I done? What do I need? 1/4 out front. You see? Because if you take derivative of that, it'll be 1 over this. Okay, great. But then derivative of the inside is 4, which I don't have, so I need to scale it. So what I'm saying is this. If you do the antiderivative of 1 over a linear expression, right? As long as that's linear down there, the answer should be natural log of that linear expression, right? Natural log of that linear expression, but I have to do a 1 over a on the outside. And this works for every linear, anytime your argument is linear and it lives inside of a function you know the antiderivative of, you can always use this same concept. Has to be linear though. Has to be linear. I'll give you one more example. How about e raised to a linear expression like that? Well, do you know the antiderivative of e to something? Itself, right? It's itself plus c. But again, because of chain rule, if we take the derivative of this, we're eventually going to take the derivative of the linear expression, which will pop an a out, and we got to kill the a. So we're going to throw 1 over a in front. So watch this. This will be our general idea. The antiderivative of some function with a linear expression inside will always be equal to whatever the antiderivative of that is, right? Which I'm going to call capital F with ax plus b plugged in, plus some constant, right? But 1 over a out front, times 1 over a out front. That is a general concept, general idea. Yes? On your formula sheet? I'll let you write that on your formula sheet. So if you have any function with a linear expression plugged in, and you know what the antiderivative of that function is, then it's whatever the antiderivative is, evaluated at the linear function, scaled by 1 over a. That's going to be useful to us because later as we move through the class, there's things we don't want to be having to think about. We just want to go right to this. It's like, oh yeah, we know how to do these. We know how to do these. All right, so do you understand why it has to be linear, or should we talk about it?
I understand.
You understand? Does everyone understand why it has to be linear and it can't be quadratic or something like that?
Why don't we?
You want to talk about it? We can talk about it real quick. Let's do an example. Let's do this one right here. Find the antiderivative of cosine of x squared plus 1 dx. Okay, look, inside of that, it's not linear, right? It's not linear.
It's quadratic.
It's quadratic. So you cannot use that formula we had, right? You can't use this. You can't treat f like the cosine function because what's in it is not linear. It's quadratic. So why is it not this answer? Well, let me see. How would we even use that formula? Sine of x squared plus 1 plus c. What would I put out front? If you're trying to use the formula in some sense, what would you, 1 over 2x? Yeah. So you'd basically be saying, everyone pay attention. What we're trying to do is think about chain rule would pop a 2x out here, wouldn't it? Yes. And we don't want it there, do we? So we put a 1 over 2x here. And you think that fixes it, right? Well, it's not a constant, but I mean, it does fix it in the sense of the idea that if I take the derivative here, imagine taking the derivative of this, right? It'd be cosine of that, great. Derivative of the inside, 2x here, right? That would be wonderful, but that's not the way I take derivative of that. It's a product, so I have to do the product rule. So it won't work. The only reason this works is because the derivative of what's inside is a constant, and that constant can be put out front, because when we take the derivative here, a constant out front just comes for the ride. It doesn't then require the product rule. All right. Okay, we are moving along. Still in the same section, substitution. Let's make that 3 minus x. One option would be to take 3 minus x and multiply it times itself 1,000 times, expand it, and then after we're done, pass an x through, and we'll have a nice polynomial, won't we? And if you have polynomial, that's additions and subtractions, right? So you can do the antiderivative of each one at a time. And you'll be there for the rest of the semester doing that by hand, right? So that doesn't seem like a feasible option, yes?
Extra credit?
Extra credit, yeah, no, that's more like torture than anything else. So the only other thing we have is substitution, right? That's all we actually talked about here, substitution. So we need to make, like, see something in its derivative, right? You can. What's the derivative of that? Negative 1. Do you see a negative 1?
I do.
Yeah, I mean, there's a 1 here, right? So negative 1 there, you're off by a constant. So we could do that, right? What did I tell you never to do with u substitution? Never to make a substitution of u as x. Don't ever do that, because all that would happen is you'd rewrite the problem, and this would be u, that would be u, that would be du. So you'd be right back where you were. So we're never going to entertain the idea of u equals x when we're doing u substitution, right? So 3 minus x seems like the next most natural candidate, right? Let's try it. It seems like maybe this isn't going to get us anywhere, right? What's the derivative of that? Negative 1 dx, right? All right. We start to run into some problems here. The good news is that this is going to be u, right? So that will turn out to be u to the 1,000th power, yeah? I have a 1 dx here, right? A 1 dx. Here I have negative 1 dx. That's easy to fix as well, right? I can just multiply both sides by negative 1. So that is good. But the problem is the x out front, right? The x out front, I can't leave it there. Your new integral can't have x's with it. Yes?
Oh, I was going to say you can just set it, solve for x.
Exactly. We're going to use this equation up here, which actually that equation creates a relationship between u and x, right? So you can solve it for u, or you can solve it for x, or you can solve it for 3. It doesn't matter what you solve it for. You can manipulate this equation however you want. So I'm going to do it this way. I'm going to move the negative x to the left, which makes it positive x. And then I'm going to move the u to the right, which makes it 3 minus u. I shouldn't write in green. It's terrible. But now I have an equation for x, don't I? So let's rewrite the problem. X is being replaced with 3 minus u, right? right here. Now, that's being multiplied, right, by the next thing. So I need this in parentheses, because that's x. What's this?
3 minus u.
No, remember in red, that's just u, right? This is 3, what did you say, 3 minus u? 3 minus 3, which it would turn out to be, I think, what you wanted it to begin with. It depends on how you said that, but yeah, you said 3 minus u, which the 3's would cancel and the double negative would become u. So yeah, you would have got there. U, it would be u to what power here? 1,000 power still. And then this became what? Negative du, right? Negative du. So let's pull the negative out front as a -1 and then du. Okay? I mean, that's what happens when we do the substitution, right? So did things get any better or not? Did the problem, did we spare ourselves any trouble, or does this still suck?
Yes and no. Like, you still have to do another substitution, right?
You actually don't need another substitution.
We could just use the, or we use log stuff to move the 1,000.
Hold on.
It's like 1,000.
No?
1,000 times by u to 1,000 minus 1. To the power of 1,000 minus 1.
Oh, like a power rule. You're saying just do the power rule.
I think so, yeah.
Well, if all we had was the u to the 1,000th, then we could find the antiderivative of that, right? But we got this. What was the problem up here? Why didn't I just do something like I told you? We could have just taken 3 minus x and then multiplied it 1,000 times, right? Nobody wanted to do that, right? Here, do we have to do that sort of thing again? No, because look at, this is u to the 1,000th, right? Times this. Can't I just algebraically multiply that through the parentheses? Right? Can I do that? Just distribute. So what happens if I distribute? I have a -1 on the outside, integral. What's 3 times u to the 1,000th power? 3u to the 1,000th power, right? Okay, and then I have minus, okay, u times u to the 1,000th is 1,001, u to the 1,001 du. Now, look at that. What do we have between them? Subtraction, which means you can do them one by one, right?
Oh, yeah.
So this I can use power rule on, and this I can use power rule on. See, this is actually really a cool problem, because this would be algebraically a nightmare, but by making a substitution, we get something that algebraically is no longer a nightmare. I'm going to do one more thing here. See if you follow me on this. I'm just doing this because this is just the way I want to do it, because I don't know. What do I do? I put the negative back in because it bothers me out there, because if I push it back in, all it does is changes signs. So I change the signs of both of these and then change the order. That's just my own personal preference. You didn't have to do that step. But now I'm not going to forget about the -1 on the outside. All right, you ready for the antiderivative power rule? The antiderivative, no more integral sign. Okay, antiderivative of that is 1 over 1,002 u to the 1,002. Right, you add 1 to that power. 1 over n plus 1, u to the n plus 1. Minus, this 3 comes for the ride, so minus 3. 3 over what? 1,001, u to the 1,001, plus c. And finally, plug u back in. What was u, right? Don't forget, you got to go back to x. So 1 over 1,002, and then it was 3 minus x to the 1002 minus 3 over 1001 times 3 minus x to the 1001 plus c. That's our answer. There we go. This one's dead. Dead. Dead, dead. Weird, huh? But cool. Weird, but cool. Now, I haven't been checking my answers, have I? I haven't been taking the derivatives of these to check to see that we are getting the correct answer. I don't know. I don't know. I'm debating. Do I want to on this one?
It would be hard to.
I really do want to do it because I want you to see not only that we did get the right answer, but I do also want you to see the algebra of it. It's not terrible algebra, but it is. It's worth seeing. Remember where we're trying to get. The original problem was x 3 minus x to the 1000th power, right? dx. So if I take the derivative of this, I better get back that, right? That's what I should get. So here I go, derivative time. So if I differentiate this, I have a minus sign here, so I'm going to do these separately. This first one, this is a constant, comes for the ride. This is something to a power. So I bring the power out. What happens when I bring that power out? Cancels out. So I'm left with 3 minus x to what power? 1001 times, now I have to do chain rule, derivative of what's inside, which is -1, right? Derivative of that's 0, derivative of that's 1, so -1. Okay, done with that one. Move on. Minus. Okay, over here, constant's going to stay here. Power comes out. 1001's cancel, but the 3 stays. 3 times 3 minus x to the 1000th power. Do I have another chain rule to worry about here? Inside, derivative of that, -1 again. All right, that's where we are. Is that this? Doesn't look like it is, right? It doesn't look like it is, but watch. I'm going to factor out a GCF from both of these, greatest common factor. Do you agree that both of those have in them a 3 minus x to the 1000th power, right? It appears here, and then I have to take one of them. I'm going to be left with one of them, right? I have 1001 of them there. So when I factor that out, what is left when I take 3 minus x to the 1000th out of this? What's left? 3 minus x and a -1. So I'm going to write that down. 3 minus x and a -1. All right, and then I have -3, and then I took all of that out, didn't I? Yeah. And I'm left with the -1 there as well. Right? Okay, let's simplify this. Distribute, distribute, and then multiply those together. So this is +3, right? And then over here, this is distribute, -3, and then what? Plus x. And then the 3's cancel. And so you get x times that, which is that. Pretty cool, huh? I mean, it works.
I think that was more difficult.
That was more difficult, the algebra? Okay, well, now it's your task to try to complete the homework for that section and do as many problems as you can. If you feel like you need more practice, you have the luxury in the year 2023 to go to Google and say, Cal 2, U substitution, practice worksheet, PDF, and you'll find 100 practice pages of problems, right? So practice, practice until you feel comfortable. Yeah. I could show you 100 more problems, and then the next problem I show you will be different, you know? So it's really you getting to a point where you're comfortable and confident in yourself, right? But the train moves on. So now we get into the next section, 6.1. So this is where it really begins for a lot of students that have not You know, in Cal 1, usually you don't get into the chapter 6. So we're about to get into our next method, technique, procedure for trying to find antiderivatives. And I think the best way to motivate it is to just put a problem up here that you can't do with anything you have, all right? So here it is. X times cosine x dx. There's nothing you can do. You cannot do them separately, right? I mean, just how great would calculus be if it were like that, right? Everyone would be an engineer, right? Everybody would be an engineer. Because that would be easy to do. You just do them one by one. But you can't, right? So then you start thinking U substitution. Do you see something in its derivative? Well, there's not a whole lot to choose from here, right? Maybe cosine? If U was cosine, what's its derivative? Negative sine. You see that anywhere? Not happening. The only other choice is x, but I already told you don't let x be u, right? With U substitution, because you're just going to rewrite the problem. So what do we do, right? We're stuck. We're stuck. So are you convinced we're stuck? All right, so if we're stuck, we need a method. We need something to do. So don't know what to do. So now comes the integration by parts. I can still remember vividly my professor, Dr. Richardson, explaining to me integration by parts. And the things he emphasized, I'm going to try and emphasize for you as well. But first, before I do that, I want to show you where it's just going to be a formula, okay? It's just going to be a formula that we use, and I want you to see where it comes from, all right? So the way I'm going to look at this is, let's say that we have two functions. Let's let the u function be some function of x, f of x, and let's let v be some other function of x. So right now, don't even be thinking about taking antiderivatives. Don't be thinking about this problem at all. Just clear your minds. I'm defining right now two functions, f and g, which I'm also going to call u and v. All right? So u is the f function, v is the g function. Got it? All right, in Cal 1, we learned the product rule, right? Remember the product rule? We loved the product rule. The product rule says that if you take two functions, f of x and g of x, and you differentiate them, right, that it's not just the derivative of each one separately, right? It's actually the derivative of f times the g function plus the derivative of the g function times the f function. Now, I believe in my Cal 1 class, I did not prove that using the limit. I don't think I proved that formula is true. I proved the power rule, and we used Pascal's triangle to do that. But I think we, as a class, voted to not prove that this is true with the limit. So I think a lot of us in our Cal 1 just took that on faith because somebody told you that's the product rule, right? So we're okay with accepting that product rule? All right, so that we've known for a while. Another way I could have written that, using this notation instead, with the u and the v, would have been this. U times v, take the derivative, right, would be equal to, what's this? U prime. I'm going to write that as u prime, and then times v, and then plus, this would be v prime times u. That's just another notation for the exact same thing I just did, right? Okay. Now I'm going to do something weird to this that you never would have thought to do in Cal 1 because you didn't know what an antiderivative was. I'm going to take, at this point, the antiderivative with respect to x on both sides of this equation. So I'm going to do the same thing to the left and to the right side of the equation. Take the antiderivative here, and take the antiderivative over here. Now, on the left-hand side, I have something, right? I have a product here, and I'm taking the derivative and then the antiderivative. So what happens when you take the derivative and then the antiderivative? They cancel, the operations cancel each other out, which means the left-hand side should just be what? U times V, right? Right? Yeah. So U times V, y'all all right with that, taking that left side, yes? No one contesting that? We're okay? Now the right side is not so simple because on the right side you have plus, right? Which means you could do these separately. But when you go here, imagine now I split this into two, all right? Imagine I split this into two. Would this one just be U times V?
That would be just time control. It would just be D.
Well, how do you undo it? See, it's not the whole thing take the derivative, right? It's only one piece of it had the derivative on it. So nothing goes away. Like you can't undo this. You just have to leave it exactly the way it is. So it's going to look like this. Integral U prime times V. That's it. That's what that is. And then plus the next one, which is integral V prime times U. See, those don't simplify. The left-hand side simplifies because it's this whole thing's derivative, then undo it. Here you can't do it because the derivative is only on one piece of the product. Are you okay with that? Sure?
Do we have to put in that second one?
Which one? The second what?
Integral sign?
Yes, because of what I'm about to do now. All right? So what I'm going to do now is I'm going to, all I'm trying to get you to do here is just believe me that this is true. That if I define two functions u and v this way, that the product rule says this, and that by doing antiderivative on both sides, I can come to this conclusion, that this is true, right? This doesn't look helpful to us at all right now, just that's true though, right? So now what I'm going to do is I'm going to isolate this on one side of the equation. I'm going to leave this one here, I'm going to move that one to the other side. So I'm going to subtract that integral on both sides, which means it'll look like this. U times v minus some integral that I don't even know, which is a derivative of u times v, equals the integral of v prime times u. That's just algebraic manipulation, right? Moving something over. We're almost there. Hang tight. We're almost there. The next line I'm going to write is so that it's going to wind up looking like the formula. Okay, that's why I'm going to write the next line. We could technically say we're done, but you know how when you have an equation like x equals 4, you can rearrange it and just say 4 is x? Like it doesn't matter which way you put the equal, right? So what I'm going to do on this one right here is I'm going to put this one on the left, but instead of writing v prime u, I'm going to reverse the order and do u times v prime.